Welcome to the Tides lecture. We're on week 11. This is a lecture using the Tides mini PowerPoint, again found under the week 11 folder. You want to remember that you do have a main Tides PowerPoint with more detailed notes and more pictures found under the Content tab. Similar to how waves began with a pretty interesting definition, tides also has a pretty interesting, somewhat difficult, although not nearly as bad as waves, definition. The textbook states that tides are a periodic short-term change in the height of the ocean's surface at a particular place. Anybody who's ever been to the beach and just sort of haphazardly put their towel down by the water's edge, fallen asleep, and then woken up wet knows exactly what a tide is. In the exact same location today, I could go stand near the water's edge and my feet aren't wet. Tomorrow, I could go to that exact same location and be under a foot, 2, 3, 4, 5, 6, 7 feet of water, and not during a storm. Periodic short-term change in the height of the ocean surface is literally remember, a tide is a wave. It's a wall of water rising and falling based on the gravitational pull, along with some celestial interaction that literally pulls the water further off the surface of the earth and therefore pulls it away from in certain sections and closer to in certain sections. So if you had a sort of half-filled volleyball or a half-filled beach ball, and you held it at, let's say, the 3 o'clock and 9 o'clock, and you pulled it right outward, what you'd be doing is pulling the sides to the right and the left further out, and the ball would essentially squish at the top and the bottom. So that means that you've pulled the height higher out, or the water level further away at the 3 o'clock and 9 o'clock, while you've squished it at the 12 and the 6, or the top and the bottom. And that, in essence, is how tides work. It's periodic and it's short term because the next day at that same time, the tide will not be in the same location. Even in an hour, the tide will not be in the same location. So it's a specific location and a specific change in the total height of the ocean surface. What's interesting, though, is that the height of the ocean surface does not all rise simultaneously or fall simultaneously. It rises and falls in certain locations. Sorry for that, I was yawning. I apologize. I'm not bored, I swear. This is the very first slide of the entire PowerPoint, so we better all be ready to go for this, right? Actually, what happened was I saw my husband yawn across the room, and you know how yawns are contagious, so it's pretty funny. Anyway, sidebar. So getting back to tides, let's move on to the next slide. I'm going to show you guys two figures that hopefully will wake me up, so to speak, but also get you interested in tides. So slide 1, slide 2. Believe it or not, same location. This is the Bay of Fundy, which has the highest change in tidal range of anywhere on the planet. The Bay of Fundy is north of us in the North Atlantic Ocean. It has a 57-foot tidal range. So at high tide, this would be the picture. And at low tide, you have a problem getting your boats out. Look where the water level has gone. It is only a 6-hour, roughly 6-hour and 12-minute difference between the high and the low tide. Now on Long Island, depending on if you're on the South Shore or the North Shore, your high and low tide difference is 3 foot, 4 foot, 7 foot in sort of the most extreme cases. This is a 57-foot tidal range. That's pretty dramatic. It also exposes the sea floor, which from a marine organism perspective is pretty scary, right? It's going to be a while if you're an organism that lives here before some water is over you again. This is also a great feeding ground and a great time for scurrying benthic organisms to be cruising around trying to feed on you, and also for birds to come eat in that soft sand. What causes tides? You guys already know this, of course. You have a general idea of what causes tides because of our discussion with the waves lecture. So it's a combination of force, of course, of the wave connection, okay, that's the gravitational force, and an interaction of the moon and sun, rotation of the earth, which again is the gravitational force. So it's a combo of both. What it's doing is it's allowing for the moon and the sun to cause a greater impact, with the moon exerting a stronger impact, about 50% stronger than the sun. Similar to plate tectonics, where we had two scientists that essentially built off of each other to give us our current model, tides function the same way. We have two scientists, one that builds off of the other, and they combined explain the effects and the daily occurrences of tides. We're going to start chronologically with Newton first. Newton coined the term the equilibrium theory of tides. This was back in the 1600s, and what it essentially does is it lets us know that the tides on the planet could uniformly cover the water only using the gravitational model. In other words, if gravity were the only thing impacting tides, water would uniformly cover the planet and the tides would rise and fall uniformly. Unfortunately, that doesn't work, and we know that they don't rise and fall uniformly. So while he was coming up with this theory, he kind of already knew that that couldn't be the only explanation, right? There had to be more to it. What he did not consider was the effects of continents, meaning where they're placed on the planet. Some are high, some are low. The ocean basin shape, all oceans are different depths, different sizes, different temperature waters are in them. And of course, the depth in its proximity to the edges of where those continents are. None of those are included in the equilibrium theory. It does, though, explain the gravitational attraction of the Earth, Sun, and Moon interaction. Again, telling you that the moon has a greater influence than the sun. So Newton is essentially saying that if you have a center sphere, that if the moon is in alignment in a straight line with the sphere, it will pull the water off. We call this a tidal bulge. This would be high tide. Notice in this particular instance, nothing is happening on the opposing side or the top and the bottom. It's just assuming that there's an interaction with the side closest to the body, right, to the moon. Second half of the story, we then realize that if this half, or tidal bulge, is pulling, then there must be a straight line interaction, which then explains that you have an equal tidal bulge on the opposite side. The combined result, of course, would be high tide at, let's say, the 1, 2, 3, 4 o'clock range, and the 7, 8, 9, 10 o'clock range, and you would have low tide in the opposing locations. The equilibrium theory, coined by Newton, assumes that the ocean is uniform, okay? Meaning it must have a total surface that is in balance, which is exactly what that picture showed us. 2 parts were bulging and 2 parts were equally flat. Unfortunately, we know that that's not how it works because the Earth's surface in this particular example is a completely flat surface with everything in equal depth and an equal distance apart. That would be as if all ocean edges, all coastal edges, were straight lines. This is the Bay of Fundy, the example I just gave you with the huge tidal range. It takes a long time for the water to get up into this upper portion, and not as long of a time to get into this lower portion. So clearly tides coming into confined areas or confined basins don't come in regularly. So if tides don't come in regularly to irregularly shaped locations, then it can't just be the Earth, Moon, Sun interaction that actually influence tides. You can go and look at any particular location, or again, you can lay your towel and wait until you get wet. But if you go and you look, you can see stain lines. You can see sort of lower stain lines and then higher stain lines. Okay. You have a spring tide or your highest high tide and your regular everyday high tide. But no matter what, you certainly have a different appearance on this piling under a bridge than you would here. This is telling us that every day, roughly, the water rises and falls this high. So we know that tides occur And we know that they're regular. And if the Earth were straight and everything were equal, this would be a perfect explanation and we'd be done. We could call it the equilibrium theory of tides. Unfortunately, that's not how it works because, again, remember, those edges are not even. So we have to counter in and come up with the missing links. First of all, there are continents that are in the way. If the water is moving and the continents are in the way and the continents aren't the same size and the edges aren't straight, then clearly that's going to impact the way the water moves. Also, the ocean basin is not flat and it's not uniform. There are deeper points and shallower points. Think back to plate tectonics. And most importantly, we know we have an average tidal range on the planet of +7 feet. If it were equal, we would literally have a 0 average range because what went up and went down would have to come to flat, which doesn't work. We have a +7 tidal range. So we know something else must be in play. And of course, what's in play are all of these points that we've pointed out here. So along comes, over a century later, along comes Laplace, the second scientist. He keeps Newton's gravitational model. He keeps everything that Newton came up with, but adds all the parts that were missing. In adding all of those parts and factoring in what we now know about waves, he renames it the dynamic theory of tides. So equilibrium implies everything is equal. We know they're not equal, so that's not a good name for it. Dynamic applies or implies change, constant change. Well, since the ocean is changing, its height, its temperature, its depth, its mobility, its location of where all of the plates are, its location of therefore where the continents are, dynamic theory has now become the current and accepted theory. You want to remember, of course, that the dynamic theory includes Newton's gravitational equilibrium theory. So Newton wasn't wrong, he just didn't tell the whole story. So now, putting everything together with our dynamic theory of tides, we have our daily tide charts. This explains, of course, how they occur. That's the gravitational Earth, Moon, Sun interaction, and then the interaction of the environment and all of the changes that occur. We have 3 different types of tides: semi-diurnal, diurnal, and mixed. Notice in the Northeast United States, where we live, we have semi-diurnal tides. So we're going to spend the vast majority of our time studying semi-diurnal tides because those are the ones that we have here. So semi means partial, di means 2, urnal means moon. So it's 2 highs and 2 lows of unequal height every lunar day. A diurnal tide means 2 highs and 2 lows of roughly equal length every day. Diurnal, right? Not partial. Mixed, as you know from mixed interference, constructive and destructive together, gives you highs and lows sort of on a changing basis. Again, we're going to focus here, semi-diurnal, partial high, partial low, 2 per day, highs and lows. What's interesting about tidal regimes, again, these are all the definitions of what we just had discussed. What's interesting about tidal regimes is that they're going to be different depending on where you are in the world. Ours, of course, is right here, 2 highs and 2 lows of nearly equal length, not completely equal, nearly equal. Each lunar day, remember a lunar day is 24 hours and 50 minutes. Diurnal, so instead of partial to moon, we just have 2 moon, 1 high and 1 low tide each lunar day. And mixed, successive high and lows in significantly different heights as opposed to nearly equal at the top. Again, this is our example. So this is where we're going to spend most of our time. So let's take a look at a lunar day. Again, a lunar day is 24 hours and 50 minutes. So a little bit past the 24-hour mark. What do we have? 2 highs and 2 lows of nearly equal height. Okay, this dot and this dot are pretty equal, although not exact. This dot and this dot, pretty equal, although not exact. Okay, 2 highs, 2 lows, partial in a lunar day. In a diurnal example, we only have, here's your 24-hour and 50-minute break, one high and one low in the same amount of time. In a mixed tide, here's our 24-hour break. This one happens to have a bunch of highs and lows. How do tides occur? Well, the bulges are going to stay aligned with the moon as the Earth rotates on its axis, just like Newton showed us. So there's a bulge, and there's a bulge. Okay, and again, that's implying that the moon is here, Earth and moon. As points on the Earth pass through the bulges, they experience high tide. So if the moon moves, the bulge moves. Moon moves more, bulge moves more. So the push and the pull are going to be in alignment with the moon. These are your high tides. These are your low tides. But similarly, if you have your highs and low tides in a semi-diurnal example, we're going to start at midnight, okay? Which is, of course, whoops, excuse me. I leaned on the screen. So if we're going to start at midnight, which is here represented by 0, but we would call it 12 a.m., right? We're going to spin on our axis, and the moon is going to stay in the same location, okay? But the moon is going to be ticking around while we spin, right? So there's two circles going on here, okay? The moon is orbiting us, and us and our moon are orbiting the sun. So we're spinning on our axis while the moon is actually going around us, and us spinning on our axis with our moon are orbiting in 1 year around our solar orbit. Okay, so we need to have 2 highs and 2 lows per day. We're saying we're starting at an island that is high and dry. In other words, this is low tide, right? The island is exposed, okay? We're going to go 1/4 of the way around. We are in alignment now with them, so we're going to have to experience high tide. The island is submerged. Now we have high tide. We're going to go around one more time. We are opposite. We are going to have low tide. Move around. We are opposite, high tide. So we went low, high in 1 lunar day. Now, what does a lunar day mean? What's interesting about a lunar day is that it takes 24 hours and 50 minutes for the completion of the cycle. Our watch, our clock, is 24 hours. So it takes longer for the moon to get around us than our preset clock time. What it does, though, of course, is it lets us know that it's going to be 50 minutes later tomorrow to be back at the same location that we started. So we have gone from 12 a.m. here, okay, to our high tide, 6:13 a.m., low tide, high tide, to our next low tide, 12:23 p.m., to our next high tide, back to low tide the next day, which has to be 12:50 a.m. low tide. Okay, so let's call this December 1st. This would be December 2nd. So we're going to be at this exact same location, at this exact same viewing, 50 minutes later tomorrow. You'll notice that as we go from each of the 4 stages, they're separated by roughly 6 hours, 12 to 6, 6 to 12, 12 to 6, 6 to 12. But not exactly only 6 hours. We gained about 12-ish minutes each time because we want to make sure that we're adding a total of 50 extra. So 12, 12, 12, and 12, 48, right? It's actually 12:30. So it's plus 12 minutes, 30 seconds each time, which gives us a total of the extra 50 minutes each lunar day. I know it seems confusing, but as you practice, it becomes really easy to understand. Okay. There's one more little sort of catch to this. Okay. If we know that it takes 24 hours and 50 minutes for a lunar day, then a lunar month or a lunar cycle is between 27.3 and 29 days. Our calendars are, depending on leap year and considering February, roughly 30 or 31 days in a month. So of course, our calendars don't match up and our watches don't match up, which is why it's so hard for us to comprehend lunar time. But there are a lot of religions that follow lunar time, and on most calendars, you can actually see when full moon is, half moon, quarter moon, right? And we think it's fascinating when we see the moon in its different phases. How we see the moon depends upon where we are in our orbit, and that actually translates perfectly with where the tidal range would also be on the planet at that time. So understanding tides allows you to understand the lunar cycle as well. This is just for example of showing you how these tides work, okay? So it's telling you that you have, this is looking up above from the North Pole like we used to do with the Coriolis effect, okay? We're spinning to the east. Our high tide is going to be at midnight, which is time 0 or 12 a.m. And therefore, it's going to take plus 24 hours and 50 minutes for the next day. So then we're going to have our next high tide at 12:50 a.m. And that is with the moon in this direct line. Influence of the sun does have some influence, not as much, about 50% as less as the strength of the moon. But what it does is it gives us constructive and destructive interference. Remember these names from waves? Remember what constructive means? Positive, that's your highest high tide. What does destructive mean? You have a high and a low, or a net zero. That's your lowest high tide. We're now going to nickname the constructive and destructive interference in relation to tides. And constructive is going to give us a spring tide, and destructive is going to give us a neap tide. Now, if we're talking about the influence of the sun and the moon, remember we had a wave that didn't match, or a wave that did, constructive and destructive. Well, if what we're going to have is our Earth and our moon, if the sun is in alignment, we have constructive interference. If, in fact, this is the moon and this is the sun, that's the same as having destructive interference because they're in two opposing pushes and pulls. Okay, so the first example, our highest high tides, those are our spring tides. The sun and the moon are in a straight line with the Earth. You're going to have your solar bulge and your lunar bulge on both sides, giving you your total highest high tide on both sides of the Earth. We find those during new moons and full moons. I hit the button, sorry. So again, constructive interference, new moon, full moon, highest high tide. In opposition, if the sun and the moon are not in the same alignment, your solar bulge pulls the water one way on either side, and your lunar bulge pulls the water another way on either side, which essentially never gives you anything equally high. And you end up with your lowest bulge. This happens in first quarter and third quarter moons. It's important that you know the lunar phase as well as the tidal result. So in a constructive interference example, when everything is aligned, you have a new moon and a full moon, and you have a spring tide, which is your highest high tide. In a destructive example, you have a quarter moon, first and third, and you have a neap tide, which is your lowest high tide. If you look over a lunar month, 27 to 29 days, you're going to have gone through all 4 phases of the moon, again alternating the new and the full with your spring tides, and the first and third quarter with your neap tides. And that means that you're going to have lower tidal heights during neap times and higher tidal heights during spring tides. You want to make sure that when you're working through this material, you're going to be asked a series of questions with the lab. You're going to be working on lab number 8 this week. When you're asked those series of questions, examples, tidal figures like this one, examples of the lunar phases like this one, and the explanation for the different types of tides like this one will all be very useful.